CHEM Lab SK015.
Alright, Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So welcome back to this channel. Okay, so in this video we are going to do the post lab for your experiment 3. Okay, determination of the molar mass of an unknown alkaline earth metal using
back titration.
Okay, as usual. So let's look at the
results.
Alright, so let's start with the first part of your experiment. Okay, titration of standard hydrochloric acid solution, where in this first part what you did actually, you were trying to standardize this hydrochloric acid solution using sodium hydroxide solution. Okay, before that, I would like to highlight this. Okay, in your manual, stated there in your manual, the concentration of sodium hydroxide, okay, was 0.1 molar, but actually what you guys were using in your experiment, okay, were not 0.1 actually. Actually it was 1 molar. Okay, 1 molar and not 0.1 molar. Okay, next is the volume of hydrochloric acid solution used in this titration. So since remember you have pipetted 25 ml, so the volume of HCl solution used in this titration was 25 milliliters or 0.025 liters. Okay, and then you're going to complete this table. Actually, this is the same table as in your previous experiment, experiment 2, the same table here. Okay, so firstly we're going to start with the gross readings. Okay, let's say this is just examples of data, so you need to use your own data. Okay, so let's say here the gross reading, the initial reading is 0.00 and the final is 20.2. okay, 20.20. So final minus initial. So the volume of sodium hydroxide used for this gross reading 20.20, 2020, same as this year, the year of 2020. Okay, so that was the gross reading. So next let's look at the first reading. And remember, gross reading, okay, is not counted. Whenever we are trying to get this average volume of sodium hydroxide, we are just using the first, second, and third. Gross reading is not included. Okay, so let's say the initial reading here is 20.20. Just a continuation from the final reading that I have obtained from this final reading in gross reading. Okay, so the initial here would be 20.20, and let's say we did the titration, and the color changes or the color change from pink, from colorless to pale pink occurred at 40.40. And we stop the titration. Okay, and then we calculate the volume of sodium hydroxide used, and let's say in this case the volume was also 20.20. Okay, so it was quite consistent if we compare with the gross reading. So the difference is less than 0.05. Okay, and then for the second reading, let's say the titration started at this initial reading 0.95, and it stopped at the end point occurred at 21.15 milliliters, and therefore the volume of sodium hydroxide used in this second reading was 20.20. Okay, see the consistency here, right? And then the third reading, for the third reading or the last reading for this part A, so let's say the initial is 21.15, and then the final reading is 41.4, and the volume of sodium hydroxide used in this third titration was 20.25. But even though the difference is 0.05, actually it's okay, because we can say that these three readings, okay, were quite consistent. Okay, and then we are going to calculate the average volume of sodium hydroxide used in this titration. 20.20 plus 20.20 plus 20.25 divided by 3, since we have 3 values here. Okay, and we are going to get 20.22 milliliters. Okay, class, so this is the average volume of sodium hydroxide used in this titration. Okay, right, so next we are going to have a look at the mass of the metal M, okay, used in this reaction in part B, reaction of unknown metal M with the hydrochloric acid solution. So since we need to prepare two pieces of metal M, okay, like this, okay, and we label them as sample 1 and sample 2. And remember, okay, before you weigh this metal M, we need to clean them up using sandpaper, and then, okay, we can bring this metal M here to the weighing room and get the masses, okay, using analytical balance. Okay, so let's say for this experiment, the sample 1 of metal M, the mass was 0.0821, while the mass of M for sample 2, okay, was 0.045 grams. And remember, since in this experiment you were using analytical balance, so your readings, your readings of your the masses, okay, must be 4 decimal points. 4 decimal points. Right. And then for the next titration with unreacted hydrochloric acid, okay, so here we have two columns, and the first column is for sample 1 and the second column is for the reaction with sample 2. Okay, so let's say for sample 1, right, so the initial reading was 0.00, and the final reading, okay, was 14.80, and we are going to get the volume of sodium hydroxide used, okay, to react with the unreacted hydrochloric acid, okay, is 14.80, and this is for sample 1. Okay, and then for sample number 2, or the second sample, so let's say the initial reading, just a continuation from here, 14.8, so here 14.8, right, and then the final reading was 32.00. So to get this volume of sodium hydroxide used in this titration with the unreacted HCl with metal M, okay, so 32 minus 14.80, so we are going to get 17.20. Okay, so once again, a reminder to all of you, remember, when you are trying to record the readings of your burette, it must be 2 decimal points or 2 decimal places. Okay, and then for this sample 1 and sample 2, no need for you, okay, to find the average of the volume of sodium hydroxide used, because we are going to use the volume separately for sample 1 and separately for sample 2. Okay, for the calculations, we are going to start with calculating the molarity of the standard hydrochloric acid solution. So firstly, before we can determine this molarity of the HCl solution, so we need to find out what are the moles of sodium hydroxide used in this titration. So to determine this moles of sodium hydroxide, simply we just use the molarity of sodium hydroxide, okay, multiply with the average volume of sodium hydroxide. So in this case, 1 mole per liter, okay, the molarity of the sodium hydroxide used in the titration, and we are going to multiply with 0.02022 liters. Okay, so for those who are still wondering from where actually I get this value, actually from here, okay, from the average volume of sodium hydroxide used in the first part of your titration, okay, in your first titration, part A. Okay, and then I just convert them from milliliters to liters. Okay, right. And then we calculate this, and we are going to get, this is the moles of sodium hydroxide reacted with hydrochloric acid solution. 0.02022 moles. Okay. Next, we are going to write the balance equation of the reaction between the sodium hydroxide and hydrochloric acid. Okay, sodium hydroxide, aqueous solution of sodium hydroxide, reacts with aqueous solution of hydrochloric acid. So since sodium hydroxide is a base, hydrochloric acid is an acid, so acid reacts with base, so it was a neutralization reaction. And we are going to get sodium chloride, aqueous solution of sodium chloride, and water. Okay, and this is the balance equation for this reaction. Okay, and then from the balance equation, okay, we know that 1 mole of sodium hydroxide reacted with 1 mole of hydrochloric acid. So it means that, okay, if we have 1 mole of sodium hydroxide, for this reaction to reach equivalence point, so therefore 1 mole of hydrochloric acid needed, okay, so to produce sodium chloride and water. But we don't have 1 mole of sodium hydroxide. The one that we are using in this titration was just 0.02022 moles of sodium hydroxide. So therefore, moles of hydrochloric HCl needed, okay, in this titration, okay, was just also 0.02022, okay, because the mole ratio of the sodium hydroxide and HCl, okay, is 1:1. Okay, and finally, we are going to determine the molarity of the standard solution of hydrochloric acid. Okay, so mole of hydrochloric acid, in this case 0.02022 moles, divided by volume of hydrochloric acid used in this titration. Okay, 0.025 liters. Remember, the one that you have pipetted into the conical flask, okay, 0.025 liters, and mole of HCl divided by volume of HCl, and finally, this is the molarity of your standard solution of hydrochloric acid, 0.8088 moles per liter, or most of you will get the value close to 0.8 molar. Okay, all right. Okay, next we are going to determine how many moles of hydrochloric or HCl in 25 ml of the standard hydrochloric acid solution that we are using. Okay, so moles of HCl pipetted is the same as the molarity of HCl times volume of HCl. Okay, so the molarity, the one that we have determined just now, 0.8088 moles per liter, times volume of acid, which is 0.025 liters, and we are going to get 0.02022 moles of HCl. Okay, so maybe you might wondering why we need to determine this mole. Okay, if you still remember, in this experiment, we did the titration twice. Okay, the first titration for part A using the same HCl solution in the conical flask. Okay, in part B also, you were using the same hydrochloric acid solution and also 25 milliliters. Okay, you have pipetted 25 milliliters of that same hydrochloric acid solution, and you were using them also in part B. Okay, so that's why the mole of HCl, okay, in this part B actually was the same as in part A, 0.02022 moles. Okay, next we are going to look at how to determine the moles of unreacted hydrochloric acid solution with metal M. Okay, so if you still remember in this part B, what you did was, so firstly, okay, you have pipetted 25 ml of hydrochloric acid, and then you mix the solution with the metal M, okay, the one that you have cut into small pieces, okay, and then you put into the conical flask. And what happened then in the conical flask, okay, this HCl reacted with this metal M. And for your information, the metal M that you were using in that reaction was not enough, so it will be the limiting reactant. So since M was the limiting reactant in the reaction, so what will happen in the reaction at the end of the reaction? Yes, okay, so there will be excess hydrochloric acid, or there will be remaining hydrochloric acid left in the flask, remains unreacted. Okay, so in this case, M was the limiting reactant, and the HCl here was the excess reactant. So right now we want to calculate. Okay, so how many moles actually of this unreacted HCl with metal M metal? Okay, so to do this, we are going to divide the calculation for two samples. We are going to start with sample 1, and then we are going to do the same thing but for sample number 2, or sample 2, and the second sample. Okay, so let's start with the sample 1. So for sample 1, okay, so from the titration in part B, moles of sodium hydroxide reacted with HCl, okay, molarity of sodium hydroxide times volume of sodium hydroxide. Okay, so the molarity of sodium hydroxide was 1 molar, and okay, remember for this titration, for the volume of sodium hydroxide, we are going to use 0.0148 liters. Okay, so for those who are still wondering why I'm using 0.0148 liters here, because this was the volume of sodium hydroxide used for titration, okay, for sample 1, 14.8 milliliters. So that's why in the calculation, okay, 0.0148 liters. Okay, so we need to use for sample 1, since we are calculating here is for sample 1. Okay, and then if we look back at the equation and the balance equation, so 1 mole of, okay, 1 mole of sodium hydroxide reacted with 1 mole of HCl. But if we calculate the moles of sodium hydroxide reacted with HCl here, okay, was just 0.0148 moles. So therefore, if we have 0.0148 moles of sodium hydroxide, so these moles of sodium hydroxide should reacted with 0.0148 moles of HCl. Okay, so if we make a comparison, remember just now we have calculated the moles of HCl used in the titration. Okay, so how many moles? Yes, 0.02022 moles. Remember, this was the moles of HCl used in the titration. Okay, 25 mils of your HCl, right? Okay, so this was the moles inside, moles of HCl inside the solution. However, once the reaction is done, so we found that the moles of HCl reacted with sodium hydroxide was just 0.0148 moles. So therefore, if we make a comparison, so moles of HCl reacted is actually less than moles of HCl available. So in this case, that's why HCl here is the excess reactant. Why? Because moles of HCl reacted is less than moles of HCl available. So means that at the end of the reaction, there would be remaining HCl, excess HCl still in the conical flask. Okay, so from here, so what we can say that moles of unreacted HCl with M metal is the same as mole of HCl reacted with sodium hydroxide in part B. Okay, just to make it clear, it's like this. Okay, remember HCl reacted with M to produce MCl2 and hydrogen gas. But in this case, not all HCl reacted with M. So there would be excess HCl. Okay, and then this excess HCl, what you guys did was, this excess HCl, you titrated this excess HCl with sodium hydroxide. Okay, so that's why the moles of unreacted HCl with M actually was the same as moles of HCl reacted with sodium hydroxide solution in part B. And that's why the value is 0.0148. So this is the moles of HCl reacted in part B, or the moles of unreacted HCl with M. Got it? Okay? Alright. From there, what we can say that therefore, in order to determine the moles of HCl reacted with sample 1 of M metal, so we can simply the moles of HCl available minus moles of reacted HCl, so 0.02022 minus 0.0148 moles, and we are going to get 0.00542 moles of HCl reacted with M. Remember, this is the mole of HCl reacted with M. Okay, right. And then we are going to do the same for sample 2. Okay, so actually the calculations all are the same with the previous sample just now for sample 1. Okay, so first we're going to determine the moles of sodium hydroxide reacted with HCl. Okay, so 1 molar times 0.0172 liters, and this actually the volume of sodium hydroxide used for sample 2, and then from here we are going to get 0.0172 moles. Okay, and from the equation, since we know that 1 mole of sodium hydroxide reacted with 1 mole of HCl, so therefore if we have 0.0172 moles of sodium hydroxide, so it should react with 0.0172 moles of HCl. And if we make a comparison between moles of HCl available and moles of HCl reacted, so we found that so the mole of HCl reacted is actually less than mole of HCl available. So therefore, what we can say about this HCl is still the same. HCl is still the excess reactant. And then we are going to determine moles of unreacted HCl with the M metal, which is the same as mole of HCl reacted with sodium hydroxide in part B. Okay, so 0.0172 moles. Okay, and finally, we are going to determine the moles of HCl reacted with sample 2 of M metal. So simply the moles of HCl available, 0.02022 minus 0.0172 moles. Okay, and this was the mole of HCl reacted. We sample 2 of M metal, 0.00302 moles. Okay, next we're going to determine the moles of reacted M metal with hydrochloric acid solution. So first thing, we're going to write the general equation between M metal with the aqueous solution of hydrochloric acid. Okay, so this is metal M solid reacted with hydrochloric acid, 2 moles of hydrochloric acid, and we are going to get 1 moles of MCl2 and 1 mole of hydrogen gas. Okay, so this is the balance equation for reaction between M metal and aqueous solution of hydrochloric acid. Okay, from this equation, we knew that 2 moles of HCl react with 1 mole of M metal. Okay, so therefore, just now we have calculated the mole of HCl reacted was just 0.00542 moles. So this is for sample 1, sample number 1. Okay, so if we have 0.00542 moles of HCl, okay, so it react with how many moles of M? Yes, we need to divide by 2. Okay, so 0.00271 mole of M metal. So therefore, what we can see here, moles of M reacted was just 0.00271 mole. Okay, so from here, next we are going to determine the molar mass of M for sample 1. So since molar mass of metal M is equal to mass of M reacted in grams divided by moles of M reacted in mole. Okay, so mass of M reacted 0.0821 grams. So divide by, just now that we have calculated, 0.00271 moles. So you divide mass with the mole, and we are going to get the molar mass for metal M in sample 1 was 30.30 grams per mole. Okay, so this is for sample 1. Right, so now let's look at second sample, sample number 2. Okay, same as the first sample. Okay, so still we are going to refer to the equation. So from the equation, 2 moles of HCl react with 1 mole of M. So therefore, okay, since for the second sample, the mole of HCl reacted with M, okay, was just 0.00302 moles, and therefore mole of M metal reacted with this mole of HCl was 0.00151 moles. Okay, and then we are going to determine the molar mass of metal M for sample number 2 here, and the mass of M for sample 2 was 0.0450 grams divided by moles of M reacted, 0.00151 mole, and we are going to get 29.8 grams per mole. Okay, so once we have determined, okay, the 2 molar masses for sample 1 and sample number 2, next is we are going to find the average molar mass of metal M. So how to do that? Okay, so simply we are going to add the mass of the molar mass of M from sample 1 with molar mass of M from sample 2, and then both of these we are going to divide by 2. Okay, so therefore 30.30 plus 29.80 grams per mole divided by 2, and finally value or the average molar mass of metal M is 30.05 grams per mole. Don't forget the unit. Remember, the unit for molar mass must be grams per mole. Okay, 30.05 grams per mole. So this is the average molar mass of metal M based on my samples or my experimental data. Okay, so you guys might get a different value based on your own data. Okay, all right. Alright, so we have come to the last part of this post-lab. We're going to do some discussions based on your findings or your results and your calculations just now. Okay, so from the calculations, the average molar mass of M from what I have obtained from this experiment, okay, 30.05 grams per mole. Okay, so therefore, if we look at this value and this average molar mass of M, okay, so we what can we say about this value? Okay, the value of the average molar mass of M metal obtained from this experiment is close to the molar mass of, right. So the first clue given to you earlier in this experiment, okay, so we knew that this M metal is an alkaline earth metal. Okay, alkaline earth metal. So what are the members of the alkaline earth metal group? So here they are. Okay, we have beryllium, we have magnesium, we have calcium, strontium, barium, and radium. Okay, so if we look at the value that I have obtained from this experiment, the molar mass 30.05, so this value 30.05 is close to, what do you think? What is the element here, okay, close to this value? If you look at magnesium, you see the molar mass of magnesium is 24.305, but from what I have obtained here is 30.05. So means that this value here is close to the molar mass of magnesium. So we can say that, okay, therefore the value of the average molar mass of M metal obtained from this experiment is close to the molar mass of magnesium metal, okay, which is 24.305 grams per mole. Okay, maybe some of you might say, why we don't use calcium? Okay, if you look at the differences here, from what I have obtained based on my calculations just now, okay, so 30.05 actually is closer to 24.305 instead of 40.078. So that's why they what can we say that here is the value actually is closer to magnesium instead of calcium. Okay, and since we knew that this M actually was magnesium, okay, so next we can say that metal M is an alkaline earth metal which is located in the which period, which block, and which group in the periodic table. Okay, so to answer this, you need to look into the periodic table. Okay, so now let's look at this periodic table. So let's look for magnesium. Magnesium, where are you? Magnesium, here. See? Magnesium. Okay, so magnesium metal, okay, is one of the members of alkaline earth metal. Okay, alkaline earth metal, and magnesium here is located in the third period or period 3. Okay, and magnesium also is located in the S block. Okay, so this is what we call as S block. So here is P block, and the center here is the D block. Okay, but for the case of magnesium, magnesium is one of the members of S block elements. Okay, and also magnesium is in group 2. Group 2. Okay, so metal M is an alkaline earth metal which is located in the third period. Okay, third period, S block, and group 2 in the PT, in the periodic table. And lastly, we are going to determine the electron configuration of M. So since M is magnesium, okay, and we knew that the proton number or the atomic number of M is 12. Okay, so M has 12 electrons. 12 electrons. Okay, so the electron configuration would be 1s2, 2s2, 2p6, 3s2, and this is the electron configuration of M. Since M is magnesium with 12 electrons.
Conclusions.
Okay, finally for the conclusions. So what can we say in the conclusions? Right, so first, the molarity of the standard hydrochloric acid solution used in this experiment is 0.8088 molar. Okay, and second, the molar mass of metal M obtained from this experiment is 30.05 grams per mole, and since this value of molar mass here is close enough to magnesium metal, okay, the molar mass of magnesium metal, so therefore we can say that metal M is actually magnesium. Right, so that's all for this post lab for experiment 3. So I'll be seeing you again in the next post lab video for the next experiment, experiment 4, inshallah. Okay, so that's all for now. Thank you and bye bye.